Hey y'all, today we're going to be discussing hybridization as well as sigma and pi bonding. So let's go ahead and get right into it. Hybridization results from the overlap of orbitals within a bond. So when a bond forms, orbitals are going to overlap. And when those orbitals overlap, the electron cloud shape changes. Now we define orbitals based on their shapes. And so when the shape changes, we have to define it in a new way. We call this a hybrid orbital. Now, when we look at hybrid orbitals, they are predicated on the number of electron domains around a central atom. So each central atom has its own hybridization. For example, if we have two electron domains, we have sp hybridization, which means we have two separate but identical sp orbitals which form. If we have three electron domains, then we have sp2 hybridization, which means we have three identical sp2 hybrid orbitals. If we have four electron domains, we have sp3 hybridization, which means we have four identical sp3 hybrid orbitals. There's also sp3d and sp3d2, depending on if we have additional domains, but those aren't really relevant for this class. You might see them, but they're not really going to be coming up very often in the class. But here's the thing. I talk about it as electron domains. When I say electron domains, that means both lone pairs and bonding domains. So if we look at water, ammonia, and methane, all three molecules have the same sp3 hybridization around their central atoms. In general, hybridization can be used to take a look at overall domain geometry, but also based on bond angles, although that's not necessarily perfect. So in general, sp3 hybridization has 109.5 degree bond angles, but we know ammonia's is less because of the lone pair interaction, and water's is even less than that because it has two lone pairs. So when we're looking at hybridization, what we're really looking at is being able to look at a central atom, assign it its hybridization, and recognize the fact that that means that the electron cloud around that central atom looks different than it did before the bonds formed. Again, hybridization is predicated on the number of electron domains, both lone pair and bonding domains. So you'll need to be able to count the domains and then assign hybridization based off of that. In this class, we're only going to be going from sp through sp3, and we will not necessarily have to do very much with sp3d or sp3d2. So with four domains, it's sp3 hybridization. But let's look at boron trifluoride, BF3. Well, BF3 has three domains due to three bonding domains, which means that we are going to look at this as being sp2 hybridization. And carbon dioxide, CO2, only has two domains. Therefore, carbon dioxide only has sp hybridization. Again, it's always based around the central atom. So when I say the molecule has hybridization, what I'm really saying is it's the central atom with that hybridization of sp3, sp2, or sp. Let's talk about sigma and pi bonding. Now, when a bond forms, orbitals are going to overlap. And we can determine whether something is a sigma bond or a pi bond based on the overlap between those orbitals. In general, sigma bonds are going to overlap more than pi bonds. And so for that reason, sigma bonds are actually stronger in theory than the pi bonds. But pi bonds are often associated with stronger bond types. And let's talk about that. So we can think of a sigma bond as being the first bond between any two atoms. So a single bond would only contain a sigma bond. Pi bonds would be any additional bonds between two atoms. So a double bond would contain one sigma bond and one pi bond, and a triple bond would contain one sigma bond and two pi bonds. So again, each pi bond is going to be relatively weaker than the sigma bond due to the fact that it is going to be less overlapped. However, by additional bonds forming, a triple bond is stronger than a double bond, which is stronger than a single bond. So when we're looking at bond structures, the strength is one element that we need to be aware of for sigma and pi bonding. We need to be able to count sigma and pi bonds in a molecule. But also we need to understand that sigma and pi bonds play a role in the process by which isomers form. And isomers, remember, are different rotations or organizations or compositions of the same molecule. Pi bonds, because of how the orbitals overlap, prevent the molecule from rotating. So you can't actually rotate around a pi bond the same way that you can rotate around a sigma bond. What this does is it prevents molecules from forming different isomers based on those rotations. Now, that's going to come up a lot more in organic chemistry than it is in this class, but that's something to just be aware of, is that pi bonds will result in fewer microstates, all right, which plays a role in entropy due to the lack of being able to rotate around a bond. That wraps up today's video. Today we talked about hybridization and sigma and pi bonding. And remember, the big takeaways from this lesson are going to be, number one, can you identify the hybridization around a central atom in a molecule? Can you identify it as sp, sp2, or sp3? Now, there are hybridizations that go beyond sp3, sp3d, sp3d2. You don't actually need to know those for this class. However, they do exist, and you might see them from time to time. So we do it the same way. We're simply counting the electron domains. So for instance, SF6, sulfur hexafluoride, would have sp3d2 hybridization because it has 6 electron domains around that central atom. Again, that's not something you're going to need to necessarily know for the exam or for the course in general, but it is good to be aware that those do exist. We also talked about sigma and pi bonding. And with sigma and pi bonding, you need to understand how the energies of the bonds differ, how the overlaps of the domains differ, and how the ability to rotate around the bond differs. You will also need to be able to count in a molecule the sigma and pi bonds. So in the end, this lesson is a little bit memorization-y, but it is an important skill to have to be able to identify hybridization and count sigma and pi bonds. So I hope you enjoyed this video, and I'll see you in the next one.